In this video, we will look at conservation of momentum. Previously, we saw the impulse momentum theorem, which related the net impulse on a system to the change in the system's momentum. From this, we can see that if the net force on a system is zero, or, and this is the same thing, if the net external force on a system is zero, then the impulse on the system is zero. And so the change in momentum is zero, which means that P final will be equal to P initial. One quick note here. Why do I say that net force on a system being zero is the same as saying net external force being zero? Well, there can be internal forces, but we know from Newton's third law that if there's a force of A on B, then there will be a force of B on A. And so internal forces, because they occur in action-reaction pairs, will cancel out, at least as far as the total force on the system is concerned. So if P final equals P initial, the momentum of the system is conserved. This might seem a little abstract right now, so let us look at an example. In example 1, we have two boxes on a frictionless table. Box 1 has mass m1 and velocity v1, and box 2 has a mass m2 and velocity v2. And the side of box 1 is sticky, so that when they collide, they will stick together. We are given the values for the masses and the velocities. And we know that when they collide, they stick together, and we're asked what is the final velocity of the system. So looking at the numbers given, we can see that M2 is more massive and is moving faster. So we can already predict that overall, once they stick together, the system should be moving to the left. But how fast exactly? Well, that's what we'll look at in this example. In this example, the net external force on the system is zero throughout the collision. There is a force of box 1 and box 2 and box 2 and box 1, but those are internal forces. The external forces are gravity and the normal force. But at every moment in time, those forces cancel out. And so the net external force on the system is zero. Since we have satisfied that condition, we know that the momentum of the system will be conserved. So P system initial is equal to P system final. Initially, the system is composed of the separate boxes 1 and 2. So P system initial is P1 plus P2, or M1 V1 plus M2 V2. The final state of the system is when the boxes have stuck together and are moving together. So when we calculate P equals MV, we are using the total mass, M1 plus M2, and there's only a single velocity since they are moving together. I plug in the numbers for M1, V1, M2, V2, and the combined mass. And, well, yes, I just have this equation. I simplify. So 5 times 2 is 10, 10 times minus 3 is minus 30, 10 minus 30 is minus 20. So I have minus 20 kilograms times meters per second I hat. Remember, momentum is a vector. And on this side, the total mass is 15 kilograms. So I have that times the unknown vector V final. So I divide over the 15 kilograms and I get V final is minus 4/3 meters per second I hat. So the kilograms is canceled. And we do see that the final velocity is indeed to the left. That is example 1. So momentum conservation is often used in collisions because if the collision takes place quickly enough, then the only noticeable forces are all internal forces. So if you define your system appropriately, so that all those forces are internal forces, then you can apply momentum conservation. However, momentum conservation is not only used in collisions. Well, think about the reverse of a collision. A collision is two things running into each other and sticking together. If we took a film of that and ran it in reverse, we would see a single thing explode into two fragments. So momentum conservation is also very useful when dealing with explosions. This will be our second example. In our second example, we have a spaceship moving through space. So it's an isolated system. There are no external forces. I should specify it is currently unpowered, so no rocket, but it has some velocity. However, it suffers a malfunction and explodes into three pieces. Piece one has a mass of 2 times 10 to the 6 kilograms and a velocity of 3 I hat minus 2.5 j hat plus 4.8 k hat meters per second. And similarly, we have the information for pieces 2 and 3. I'll just pause here a moment so you can look at the information. The question is to find the initial speed of the spaceship. So since there are no external forces and the force of the explosion is all internal, right? It's, force of piece one on piece two and piece three and vice versa, and force of piece two on piece three and vice versa, and so on. Then the system's momentum is conserved. So P system initial equals P system final. And P system final is equal to the sum of the momentums of each of the pieces. So M1V1 plus M2V2 plus M3V3. Remember, these are vector quantities. Plug in the values that were given. Not going to go over all the arithmetic in detail. I'm just going to show it on the screen. You can pause the video and check it out. Let me know if you find any mistakes. And so we add all that up and we get the total system momentum in the end is this quantity. All right. Well, what about the initial momentum? Well, initially the spaceship is all one piece, and so we can add up the masses. We're assuming that no mass was lost in the explosion, and we get this total mass, and we're trying to find the initial velocity first, and then the speed. So P system initial equals P system final. We have M total V initial equals P system final. V initial equals P system final divided by M total. And we plug in the numbers and simplify to this result in meters per second. So this is the initial velocity. It's a vector. We're asked for the initial speed. So we take the magnitude. And that gives us the result of 37.1 meters per second.